Okay, so welcome back to another video. So here we have a little long summation, well, difference of sums that we would actually like to evaluate / simplify. And we have 20 times the infinite sum, k is equal to 1, of -1 to the k plus 1 divided by 2k minus 1 times 1 divided by 25 to the power k. Subtract 239 multiplied by the infinite sum of the same index as before of -1 to the power k plus 1 divided by 2k minus 1 multiplied by 1 divided by 57,121 to the power k. So as long as that sounds, how is it even possible to simplify? And well, this wouldn't be a video if that wasn't the case. So yes, this can be simplified. So using a lot of, well, that part actually comes for the last step specifically. We'll be using a bunch of trig identities, but really the first couple steps we'll be doing is manipulating, this infinite sum each at a time, and then using a little bit of calculus to, further enhance the simplification a little bit better before heading towards that trig identity. So there's also some interesting things to note that specifically 57,121 is actually can be rewritten as 239 to the power square. So that's another, that's one thing that's very helpful for us for our procedure. So anyway, anyways, it's all just simplification from here. So sit back, enjoy the ride, learn something new, and let's actually just jump right in. So this entire thing, I'm going to call this capital A. So let me actually first write that note that I just said, that 57,121 is equal to 239 square. And so with this, let's actually set the following function. So we'll call this f of x. We're going to let this equal to this following infinite sum. So we're going to say that, again, same index, k is equal to 1 to infinity, of -1 to the power k plus 1 multiplied by x to the power 2k subtract 1. All this divided by 2k subtract 1. And so from here, I'm going to call this A. And if I could just rewrite the whole thing again if I want to, but I'm just going to skip that and then jump to some discussions that we're going to make with these steps. First off, what I can do is to make the simplification a little bit easier, and so that it's helpful to use our following function f of x. Let's divide 5 to both sides over here. So that means this is going to be 4. And of course, we still have the infinite sum over here. So k is equal to 1 of -1 to the power k plus 1 divided by 2k minus 1. And so if I divide the 5, so really that 5 has to go back into this over here with the same base, since 25k is the same thing as 5 to the power 2k, but then associate that with the division of 5 over here. So now let's actually put that with the exponent of subtract 1. Now that this is out of the way, so let's actually now focus on this. Again, we can actually apply the same method. So I'm actually going to move on to the next line over here. So subtract. So let's divide a 239 over here. And this is helpful to say because since we said that 57,121 is the same thing as 2 to the 39 square, then we can actually rewrite this piece a little bit easier. So again, same summation, k is equal to 1, -1 to the power k plus 1, then divided by 2k minus 1, then multiplied by 1 divided by, so divide the 239 both sides. So we'll have 239 to the power 2k and then subtract 1. And so with this, so we can actually notice that specifically f of x is written as, as the following function as we want to write. Notice that if I actually plug 1 over 5 for our input, this is exactly what we get over here. And if I were to plug 1 over 239, this is what we get over here. So in other words, I can write this as in terms of f of x with the inputs. So this is the same thing as 4 times f of 1 over 5. Then subtract f of 1 over 239. And so with this, now we can actually do some simplification from here. Well, first things to note is that, again, we can actually plug f of x, so x is equal to 0, and then what do we get out of that? We actually get that it's going to equal 0. So let's actually make that important note. This is going to be very helpful actually in the next step specifically. F of 0 is going to equal 0. And so moving on from here, so there's got to be some way to actually evaluate this. Well, here's a little bit of a creative approach we're actually going to make from here. Actually, not just yet. Next thing what we're going to do is, and then afterwards is actually going to be a very helpful step. So what I want to do now is let's actually differentiate both sides with respect to x of our function. So specifically we have that f prime of x. Okay, so that means let's just use the power rule over here. So just 2k minus 1 to the front, that gets rid of itself, and then plus or subtract 1. So we have that this is the infinite sum from k is equal to 1 of negative 1 to the power 2k, or excuse me, k plus 1, and then multiply by x to the power 2k, and then subtract 2. What I can do from here is let's actually do a little bit of re-indexing. Not in the sense that we can actually do a substitution, but so to the fact that we can actually make the equality the same. And you can see why I say not necessarily substitution. See, what I can do here is that now with our new index, if I start this with m is equal to 0, then anything if I plug for 1 back into here, notice that this is actually going to keep, this is going to start off as an even term, or rather, it's going to be 1, positive 1, not negative, excuse me, this, because this is alternating for 1. So I'll have that this is going to be started with negative 1, then to the power m, notice that matches. And if I do the same thing over here, so k is equal to 1, so that means we have 2 minus 2 is 0, so I'll put this as x to the power 2 times m. As if I go to the next index, then it just that actually as doubles. So in other words, we have this, then interestingly you see that this is going to work since we have everything strictly less than 1. So if you look closely, we have a in a form of a little geometric series that it's actually less than well, the absolute value of x is less than 1. So if you see what I can do with this, so we have that this is actually negative x, or negative x squared, then that means we have that this is equal to 1 divided by 1 plus x squared. Now we have our differentiation, so now we can now pay attention to something in the form of rewriting f of x. So notice that f of x can be rewritten as f of 0, which we said that's equal to 0. And then if I were to say that this is plus f of x and then minus f of 0, again, 0, 0, same thing. But you notice that we can actually see that this can be rewritten in the form of an integral using with the whole, fundamental theorem of calculus that can say that we have that it's f of 0, which is equal to the integral from 0 to x in respect to t. So f prime of t dt, an antiderivative exists, so perfect for that. So in other words, I can actually now say that this is supposed to be a plus over here. I wrote 2 equals by mistake. Then with this, we can say that just substitute the f prime of x, well, now in this situation in the world of t, so this will be from 0 to x of 1 divided by 1 plus t squared dt, which we know that that antiderivative exists, that this is actually just inverse tangent of x. So with this, now going back to our a, which we said that this is equal to 4 times f of 1 over 5 minus f of 1 over 239. So we can actually substitute everything for the f of x for in terms of tangent x, inverse tangent of x, and then with the input. So with this, a so far is 4 times inverse tangent of 1 over 5, and then we subtract with inverse tangent of 1 divided by 239. So now with this, here comes the trig identities that we will be using, but we have to take a little bit, we're gonna have to slow things down just a little bit, because what we can do from here is that now that suppose that so far we have a is equal to this following, let's do a little bit of a substitution. Suppose that if I let u equals inverse tangent of 1 over 5, and then if I let v equals inverse tangent of 1 divided by 239, okay, then so far that has to mean that we have that a is equal to 4 times u and then subtract v. So let's take the tangent of both sides of the equation. So I have that tangent of a is equal to tangent of 4 u minus v. That's actually going to have to require a, that's a difference identity for tangent, but we actually had to figure out what the 4 over u is equal to. There's a formula, of course, that exists for this, but we have to calculate like the smaller things, of course, in order to reach that what we want to do. So let's start off with the double angle identity. Specifically, we don't really need to do much with the v substitution, but it's more of the for u we have to, pay attention closely. So we want to start small with that. Double angle identity will start is that tangent of 2u, we know that that formula exists, and that says that this is equal to 2 times tangent of u divided by 1 subtract tangent square of u. And so if I just plug in that we said that tangent of u, and so we say that if tangent of u, specifically if I just take the tangent both sides, so that means we're just left with the inputs itself. So that means I have 2 times 1 over 5, so that's 2 over 5. And then we divide this by 1 subtract tangent square of or well, specifically this is 1 minus 1 over 5 squared, or 1 over 25. And so from here, if we actually simplify all this out, we'll get that this is going to equal 5 divided by 12. Okay, so not much yet, but now we can actually do this again for tangent of 4u, which is what we want from over here. But basically, it just follows that same identity, except you just plug the input for, 2 twice again. So we have 2 times tangent of 2u, and then we divide this by 1 subtract tangent square of 2u. Okay, and so with this now, if I just plug this back in, so it's 2 times, so we know that tangent 2u is equal to this same thing, so it's again just do substitution. So we have 10 over 12, so it's 2 times this, all the way with divided by 1 minus tangent 2u, so square, so this will be 25 divided by 144, which if we simplify all this out, we'll get that this is equal to 120 divided by 119. So we have our values for specifically for tangent 4, and then the v will come in handy in the next step. So with this, now going back, let me just switch to another marker. Now going back to our tangent of a is equal to tangent of 4u minus v, then we have that the identity, specifically the difference identity, says that, so let me put that back in, tangent of 4u subtract v. This is going to equal this identity over here, tangent of 4u subtract tangent of v, then this is being divided by 1 plus tangent of 4u multiplied by tangent of v. Okay, and so with this, now we can actually plug in our substitution. We know that tangent of 4u, we said that this is 120 divided by 119, then subtract the v, or specifically tangent of v, so that means that gets rid of itself and we have the input. So that'll be 1 divided by 239, all this being divided by 1 plus tangent u, so 120 divided by 119, then multiplied by 1 divided by 239. So this kind of looks a little hefty to calculate. So, but let's actually jump into the whole simplification from here. So far, I'll take things one step at a time and slow it down. So if I actually just cross multiply from the top, so I have 120 times 239, then we subtract with 1 times 119, and all this being divided by, cross multiply 119 times 239. That's just for the numerator. And then we fix the denominator up. So we have, again, just make sure that we write this in the same denominator, so it's because it's 1. So I have 119 times 239, add this with 1 times 120, and then all this being divided by 119 times 239. And so with this, so let me actually move that equal sign. So the equal is supposed to move over here. So equal sign, okay, so let's actually fix this up. So these denominators cancel, so we're literally just left with the both the numerators from both the numerator and denominator. So 120, 239, and subtract 1 times 119. All this being divided by 119 times 239. Add this with 1 times 120. Okay, so this kind of looks difficult to achieve from here. That's okay. What we can actually do here is I'll actually factor out 239, so one quantity of that. So in other words, I'll write this as 119 then times 239. If that's the case, then that means I factor out one quantity of that, so that means I have to add an extra 239 to preserve that equality, then subtract with 119. All this being divided by 119, then times 239, then plus 120. Okay, this is interesting to see because 239 minus 119 is 120. That has to entail that this is actually the numerators and the denominators share the same value. In other words, it just cancels each other out, which means it's just equal to just 1. And so with that, tangent of 4u minus v is equal to 1. So tangent of a is equal to 1. I guess I have it over here. Tangent of a is going to equal 1. Take the inverse tangent of both sides, so that means a is equal inverse tangent of 1. In other words, this just comes down to just pi divided by 4. And just like that, we have finished the simplification, the long simplification of the difference of sums, infinite sums, and it actually, comes down to a very nice answer. Leibniz's formula for pi, if you want to put it into that perspective. So yeah, that's pretty cool if you ask me.